Okay, this is by Boscovich, mentioned in the quantum physics book. The book is called The Quantum Dice by this person, and it's at this web link here. And Boscovich doesn't get mentioned in many quantum physics books, so this is why I'm bringing it to the attention. Right, here we go to it now. So that's who it is. It's Professor Leonard Pon Ponmaru, born in 1937 in Donbass in the south of Russia. In 1963 he graduated from Moscow University and for 20 years worked at the Joint Institute for Nuclear Research, so at Dubna. So we go to the bit where he's got about Boscovich. This is highlighting information about Boscovich. Here we go. So it's what it's got here. It's the life of Boscovich. Roger Boscovich, 1711 to 1787, is now known only by a narrow circle of experts, but early in the 19th century he was a celebrity, and his theory of the atom influenced the thinking of such men of science as Faraday and Maxwell. So it would go down to his theory. Of the few who in the 18th century believed in atoms, Boscovich was the only one who did not think of atoms as tiny solid balls. His views were rather close to ours than all the atomic theories of the 19th century. So really it was Dalton who's given us the idea of the chemical atom, but when you think of an atom in the sense of the original Greek, it's something that can't be split any further, and so this is what the idea of Boscovich was. It's for an atom which can't be split to something smaller. His argument against the hypothesis of incompressible ball-shaped balls were as follows: it did not account for the crystalline structure and elasticity of bodies, the melting of solids, the evaporation of liquids, and especially chemical reactions between substances constructed out of these round, solid, impenetrable spheres. So he goes against the solid ball theory. And let's go on to Boscovich's theory. Boscovich pictured the atom as being the centre of forces that vary with distances from the centre. So what he's talking about we would probably now call point particle. Near the centre, the forces are repulsive, which corresponds to the repulsion of atoms or point particles when they are brought into close proximity or collide. As we move away from the centre, the repulsive forces first decrease, then vanish, and finally become attractive. According to Boscovich, solids change into liquids and vice versa, exactly at the moment when the forces change their sign. Still farther away from the centre, the forces again become repulsive, causing liquids to evaporate. Lastly, far away from the atom point particle, the force is always attractive in accordance with Newton's law of universal gravitation. So far they get away, eventually it's Newton's law of universal gravitation. And I think really, which is not mentioned here, but universal gravitation by Newton does vary a bit as it gets further out. Each of Boscovich's atoms, which are the point particles, thus ascends to the very boundary of the solar system, and since centres of force can neither be destroyed nor created, the atoms of Boscovich were eternal, just as those of Democritus. It was this part of Boscovich's theory that was especially congenial to Faraday. We can readily see its analogy to Faraday's idea of the lines of force of the electromagnetic field, and later on, at the turn of the 20th century, Lord Kelvin once again turned to the atom of Boscovich, point particle, in his attempt to explain the nature of radioactivity. Boscovich's atom, this point particle, is a good deal closer to the modern atom, thinking of point particle, than Democritus. Like the modern atom, should be better set called point particle. It has no definite geometrical dimensions. On the other hand, it helps one's understanding of the variety of crystalline shapes and chemical transformations in which these atoms, i.e. point particles, take place. The atom of Boscovich point particle is clearly a speculative scheme which is based neither on experiment nor mathematics, only on common sense and keen observations of nature. Well, point particle is a mathematical thing anyway. Boscovich wrote, "There are indeed certain factors regarding the law of forces of which we are all ignorant. They are concerned with intervening arcs and other things of that sort. This all, however, far surpasses human understanding, and he alone, who founded the universe, had the whole before his eyes." So the capital H for he, so it's meaning God. Quantum mechanics enables us to derive the law governing the variations of the force between two atoms, i.e. point particles, without any arbitrariness or any reference to divine prevision. We can use the law of forces to predict the spectrum of the hydrogen molecule and calculate the energy needed to separate one hydrogen atom from another. We can even foresee the results of mixing hydrogen with, say, chlorine, and what will change if we expose this mixture to ultraviolet radiation. We are able to determine the shape of crystals and even to predict the colour of chemical compounds, which when I say we, I mean of course those conversant with the fairly complex mathematical tools of quantum mechanics. Anyone, however, who is in the least bit acquainted with its images can readily understand many of the features of the structure and properties of matter. So basically, really, the point particle idea of Boscovich goes on to be used within quantum mechanics. It's the basis of modern quantum mechanics. I don't know if this Russian bloke is really saying it that well, but you've got the problem with the word atom, meaning what Dalton there means as a chemical atom, the atom of a chemical element. So the original Greek being that it was a particle that can be broken down in further. So there we go. That's interesting, isn't it?